There we go.
Yeah, it's a thing that I think is developed mostly by Christian theology. It's like these are the unforgivable things that people can do, and the dungeon they're going to basically attunes itself to different sins, and I have to determine which one they are most aligned with.
How many people are doing it right now?
For 4 ambies. It would be really interesting if there's 7 and they actually all just one in each, but that would be unlikely.
That's a lot of effort, but it's fun.
Yeah, it's a lot of fun.
All right. Well, we are in Canvas right now. Somebody was mentioning Raspberry Pi GPIO access. You're poking up to the input-output ports of a Raspberry Pi. So I found a little bit of information on that one, which is kind of interesting and somewhat related to this class. So as it turns out, there's an article that talks about how to access the general purpose input-output pins on the Raspberry Pi, but only as a file, which is the usual things that Linux would do, or Unix, any type of Unix system would do, is if you have any system resources that you want the end users to have access to, they will basically turn it into a file operation. So when you click on this article, it shows you how to do it. It's pretty old as an article, but oh, okay. Huh?
You accidentally put the parenthesis inside the link URL.
Oh, okay. So I'll still open it as a new tab, and then just change that part. There we go. There you go. So it's just a file operation. So there's a special file called /sys/class access GPIO. Has 2 files, export and unexport. So it basically gives you the ability to use just normal file operations to get the status of the pins and also to control the voltage on those pins, turn it on, turn it off. But this is a pretty standard way of Linux or any type of Unix system to do things. They try to map everything to the file system itself. So there are so-called files inside Linux/Unix that are not really files. They're really system resources, but they are in the form of files so that any program without special libraries can interact with those things. For those of you who are transferring to SACState, there's a class called Systems Programming over there. We used to offer the same class over here, but because of low enrollment, we do not offer that anymore. It might even be deleted from the catalog. But in that class, we kind of talk about these concepts a little bit, and to me, it is a lot of fun. That's a fun class to teach. Okay, so that's that. And then we go back to the modules. And if you guys have any questions about the homework assignment, the Music Box homework assignment, let me know. If not, we are going to start with studying the RAM module in Logisim as well as MUX and DMUX in that library, because these two are the last 2 components that we need in order to understand how components inside the processor operate. So in this class, you're not going to design a processor; it's already done. Okay, but what I will present to you does require you to understand all of these components first. Is that okay so far? Does everybody understand kind of the big picture? I will give you a processor that works. It's all done already, but you have to understand how the components inside that Logisim, pretty big Logisim file, interoperate. And then your job is to write the microcode, a little bit of that, and also to write actual instructions to make it go, to do certain things. All right? Okay. So let's go to Logisim right now and take a look at how RAM operates. Now, since I already have that moved into a folder, we can actually do it here. Now, how do I open a file from here? Well, I guess I can always go to a command prompt. Okay, go to Logisim, go to doc. How many people did this part already? Basically just unzipping the jar file to get to the HTML documents, okay? So was it doable? I mean, just rename the file to a zip and then just unzip it? Yep. Were you guys surprised, or did you know this already from your Java class?
I didn't take Java, but I knew that you could do it.
Okay. You can probably just Google it too,
Yeah.
you know. Okay. So we'll go ahead and go to HTML and do a Firefox on index.html. There we go. So what we're doing is we're going to the library reference, and then we want to go to memory library and go to the RAM module. So I'm doing this, you know, using a browser instead of using Logisim itself, because if I use Logisim itself, I can't really zoom in. I have no control over that internal browser. But here, you know, I can just zoom in, you know, to as much as I want. So what you can see here is a memory module, and a memory module, I'm not sure how much you can see in terms of the details. All of these little dots here, they are all individual points that you can connect something to. And I think they have changed a few pins, you know, maybe not, I don't think so. Okay, so A is the address point. So, okay, internal to RAM, you have locations. So depending on the width of the address port, that determines the number of locations inside the RAM module. If your address has 8 bits, for instance, there will be 256 locations in that particular memory module. If you increase the width of your address to 10 bits, then you have 10 to the power, excuse me, 2 to the power of 10, which is 10,024 locations in this RAM.
Is it 10,024?
1,024, thank you. 1,024, 1024, but not 10,000. There's 1,024 locations. They're numbered from 0 to 1,023, but you only see the hexadecimal version of those addresses when you're inside the RAM editor. So that's A. The other ports we know already too. Just like ROM, it has a data port, but this time the data port is a little bit interesting because it is bidirectional. Because what is the difference between a RAM and a ROM module? What is the main difference? Sorry? You can write to RAM. You can change the content of RAM. But with ROM, you can only read, right? Because that's the whole name, read-only memory. Okay, so that means with the ROM, the data port is always upwarding. Okay, if you enable the ROM, the data port is driving the lines. Okay, it's trying to specify a 1, a 0, and a 1, and 1, and so on. But in the case of RAM, the data port is bidirectional. Okay, it can both read, it can also write too, depending on whether you're specifying a read operation or write operation. The read and the write operation is always from the perspective of the processor and not from the perspective of the RAM itself. So when we say read, we are basically saying read from memory. So the RAM is actually driving the data bus. When we say write, we are writing to the memory module, which means the data bus is actually, you know, high impedance and is actually reading what you specify as the processor. So are we doing okay so far with the address and the data ports? Yes? No questions? Yep.
So is that ROM on the left side and the RAM on the right side?
No, they're both RAM modules here, and it has two appearances. The change is the IN here. There's no IN in this one. And the other one has the IN. That's the only difference. Okay. Now this pin here, SEL, is also present in the ROM module. Cell is select. Okay, it is the same thing as what we in industry they don't call it select, they call it chip select. Okay, CS, which is chip select. So select basically is saying, are you being addressed? Okay, RAM module X. Okay, should you pay attention? So if cell is low or 0, it means this memory module should not pay attention at all. Okay, I'm not talking to you. When the cell is a 1, that means I'm telling this RAM module or ROM module in this case too. So I'm telling this module and saying, okay, you pay attention to the address bus and all the other pins because I am talking to you. Okay, I want you to do something. So cell allows you to have a multi-drop type of configuration, which means you have multiple memory modules. All the address bits and all the data bits are connected the same way. It's a multi-drop setup. but by using the cell or the chip select line, they can share the same bus, but only one will talk at a time, so it's okay. Is that okay so far with that idea? Okay. The next one is, okay, I'll let you guys guess what this one is, because we've seen it already in your homework assignment. What is it? It's a clock, okay? So the clock is missing entirely in the ROM because it is only used when you're updating the content. You cannot update a ROM, okay? But not when it is deployed already, okay? But you can update the content of RAM, and as a result, we have a clock line. It is the same setup as with a register. It is edge sensitive, and I think you can also configure this one to be rising or falling edge sensitive, but you have to pick one or the other. So are we doing okay so far with the clock line? Is that okay? All right. So the next one is called out. This one allows you to specify, are we doing a read operation or are we doing a write operation? So out is supposed to be a 1 when you are reading from RAM. We can read the documentation later because I always got it confused. But basically it specifies, are we reading or are we writing? Are we updating the content of this RAM module, or are we retrieving information from this particular RAM module? The next one, we have seen it also with a register. Yep.
So I pulled one up on Logistim, and it doesn't have out, it has LD.
Yeah, same thing.
Same
LD is
thing.
load, you know, it does the same thing. So this documentation may be dated, you know, that's why it's inconsistent. CLR is clear, which is also known as reset, which is also labeled 0 with a register. What does that do? It empties everything, well, it doesn't really empty, but it turns every single bit within the RAM module all to zeros. Same thing that it would do to a register. So are we doing okay so far with a RAM module as far as the ports are concerned? Sort of, okay. So in case you have questions about those, you can always just read the documentation. You know, this is a general description, and this is a picture. You know, we'll do a little demonstration, so don't worry about, you know, oh, but I don't know exactly how it works. We'll figure out how to get it to work. So the pins are, you know, one is A, which is the address pin. D is a data pin. So those two, we kind of know what to do with those. And then we have cell, which is select, chip select. And then we have the clock line, which is the triangle on the south edge. So the only one, okay, it says LD here, not out. So the documentation is not even self-consistent with its own bitmaps, unfortunately. So LD is controlling, are we doing a read operation or are we specifying a write operation? And the terms that it uses is a little bit confusing. Select whether the RAM should emit or should it be the value of the current address bus. This output behavior is enabled if out is 1. So you can see how it is inconsistent even within the text here. It says LD here and then it says out here. So if LD is 1, the output is enabled. If out is 0, then it is a read operation. So LD is a 1 means the chip is outputting the content, which means you're reading content from the chip. If LD is a 0, it means you are writing to the RAM. So the RAM is actually reading from data port D. Is that okay? So in industry, they do not use the term LD, load, or out. They use read-write. So typically in this case, it will be R/W. Okay? So R/W has a particular meaning. Let me write it here, what I mean by that. Okay, there we go, mouse pad. So the so-called LD pin is called R/W in industry. Okay, so most people look at R/W and go like, oh yeah, we know what it is. It's read or write, okay? Well, that's one interpretation. But this actually has a special interpretation because R/write basically means, you know, R is specified when the pin is 1, and then W is specified when the pin is a 0. Because /W means it is active low, which means when the pin is low, you are specifying that operation. So /W means a write operation is selected when the pin is a 0, which is the same thing as what I'm putting here. Okay, do you guys have any questions back there? Because I saw you guys kind of conversing a little bit. Nothing for me? Okay. Is that okay so far with the load pin? Because that's not standard, it's not industry standard terminology. And cell is called chip select in industry. Not just select, but chip select. But that's just minor things, nothing that you won't. There's nothing here that you won't learn later on when you're actually in industry. Yep.
What's the point of having input in if you can just specify read or write with just out?
Input.
Yeah, on the in the picture on the right side, it had the.
Oh, you mean here?
Yeah.
This one has 2 pins. It has got 2 data ports, one for reading and one for writing. So in is basically saying, are we doing input or output? So it is actually described here a little bit. We're not going to use this one. This is definitely not very industry standard. But it does, specify the in pin later on here. Okay, right there, I think. Store this pin is present only if separate load and store ports is selected for data interface. When it is a 1 or floating, a clock pulse will result in storing the data found on the west edge into memory. Okay. So it seems to be a duplicate to me. But it's only useful when you have separate port, 2 data ports, one for reading and one for writing. I'm assuming there's one chip, memory chip, that behaves exactly like this, and that's why it is included into the library. But typically, we don't use memory chips like that. All right. So are there any questions about the pins of a memory module? No questions? All right. So let's go ahead and just kind of experiment with it. And this is something that I do encourage all of you to do. Whenever you learn, you're exposed to something new in this class. So the way you kind of learn it is to read about it first, and then you just play with it. Okay. So you say java-jar, and wherever the file is located. Because I don't know how other people learn, but this is how I learn. Is I just read about it. I seem to get an understanding of what it is supposed to do, and then I will use experiments to confirm my understanding is either correct or incorrect. So we go to memory. We pull a RAM module out of it, kind of smack it, put it here in the middle. So when you look at a RAM module, it has got certain properties. It has got the address width, which in this case is 8 bits. So that means we have 256 memory locations. Each location has the width that is specified by the second item, which is data width. It's the same as ROM, okay? And this one you can also set it to some really odd, width, like 13 bits, okay? We typically don't use these really odd numbers because 8 is 1 byte, so we typically use 8. And data interface, in this case, we're using one synchronous port for data. So you can see that there are 3 options. To see the actual 3 options, we can increase this width here, and then we can click it. So you can now see one is one synchronous load store port, and then the other one is one asynchronous store load port, and then you can also have separate load store port. The difference between sync versus asynchronous is synchronous means it is clocked, okay? So it is synchronous with other components in the system using the global clock signal. Asynchronous means, whenever you specify new content and the enable is high, we're going to store it, okay? So most of the time you want to use synchronous operations when it comes to memory modules. So we do okay so far with all of these properties of a RAM module. Okay. So in this class, this is what we're going to use, synchronous load store port. So now we can just kind of play with this. We'll start with something simple. Okay, we'll start with a pin to go into the address port, and of course, this has to be 8-bit wide to match the width of the address port. With select, we'll have another pin. Okay, so this goes to select. With clock, we'll actually get a clock pin so that later on, if we need to automate things, we can just make it clock automatically. So I think that's under wiring. Yep, there we go. Put a clock here. And then we have 2 more pins to specify is it a read or write operation. And yet another one here to specify are we resetting the RAM module. Okay. And then we want to look at what is presented on the data bus. But now we have a little bit of a problem. Should I use an output pin to connect to this thing, or should I use an input pin to connect to this thing?
You do like an OR gate and connect to both?
Well, we need something that is different from just an output or an input pin.
Transistors for when it's on and off.
Hmm?
2 different transistors, so an N-type and a P-type, so when it's on and off.
No, I don't think that's what I'm asking. I'm asking what should I...
Like a splitter?
Not a splitter. Splitter won't help here. Okay, let me show you what the problem is. Okay, I specify that. Okay, there we go. So right now they're all X because the RAM module is not even selected, right? Because if you look at the select pin, it is connected to a. If you look at the select pin on the memory module, it is now connected to an input pin that is currently specifying a 0, which means the chip is not even selected. If the chip is not selected, it shouldn't do a single thing. Okay, it should not specify anything on the data port, and that's what you're seeing with all the X's. It means it's high impedance and nothing is specified. Is that okay? So it's just floating. Okay, in electrical engineering terms, the data bus is quote unquote now floating. Okay, if you put your computer next to a microwave, you will start to see zeros and ones. If you move it away from the microwave, you will see something different. Okay, so it's just not being specified right now. Okay, so let's see what happens when we specify a read operation. So when we want to specify read operation, we should first say yes, turn on. And you can see, as soon as you turn on the chip, whatever you specify with the address is now selecting the location in the memory module. In other words, it is now interpreting the A port, the address port, so that it says, oh, okay, you want to get to location 0. Location 0 is now specified. But you can see the output port is still all X's, because at this point, what is LD? LD is a 0. When LD is a 0, remember it's R/W, it is selecting the quote-unquote write operation right now. Okay? But we want to do a read operation. Okay, so let's go ahead and specify read operation. So we have to turn LD into a 1. Now you can see the output is driven because it is saying, oh, location 0 that you asked for, because the A port has 0, has a content of 0. That's all it's saying. Are we doing okay so far with this operation? It's a simple read operation. Okay. So what do I do to change location 0 to, let's say, 4/6?
You just like add an input pin right next to the output pin, and that will work.
We can do that. Okay, so let's turn off these things first, and then we add an input pin. Okay. Make it 8-bit wide, and hook it up. We'll hook it up like this for now. Okay, so we can now specify. It's gonna have a little bit of a problem later. Okay, so you can see as soon as this is hooked up. Okay, if I take out this pin, you can see this particular output pin are all X's because no one is driving it. Okay, no one is saying okay you should be a 0 or 1. It's just floating. The input pin is driving. So as soon as you connect the input pin to the output pin, the input pin is driving the output pin, and that's why you see all the output pins having the same content as the input pin at this point. Are we still doing okay so far with this? Okay. So we'll carry on our operation. 4, 6 is a 0, 1, 0, 0 for the high nibble, and then a 1, 0, 1, 1, 0 for the second nibble, and you can see that's being done here. So to store that into location 0, location 0 sounds really boring to me. Pick something else. Pick something that is in this picture.
Location 6.
Location 6? Okay. So we'll specify location 6. So we put 6, which is 0, 1, 1, 0, into the address port. Okay. Now you say, okay, RAM module, pay attention. Oh, I'm paying attention. You are specifying location 6. So now the RAM module is saying, okay, I'm flipping to the right page already. You just said page 6, I'm on page 6. But it doesn't know what else you want to do. Okay, so at this point, it is making the assumption this is a write operation because the LD pin has a value of 0. Okay, but it's not doing it yet because when you specify a write operation, it is synchronous, it is waiting for the clock to have a rising edge. Okay, the clock is currently stable, low, so nothing is being done. So the moment we change it to high, oh, okay, so now it is 4, 6. It takes in whatever is presented at the data port and update the selected location to that content. Woohoo, done. Okay, so now we want to turn it around and say, oh, we want to do a read operation next. In fact, we want to read from location, I don't know, that's the 0D, okay? So we want to read from location 0D. So most of the time, when you do something in between, you want to turn off the select, and the clock signal would turn off by itself because it is just cycling on and off and by itself. So now we want to select location 0D. D is 1101. Okay, there we go. And then we turn on the chip, and it is now selecting that location. But at this point, there's no problem yet because LD is still a 0. In other words, at this point, the chip is still assuming this is going to be a write operation to change its own content. But then we correct the chip and go like, no, we want to read. Okay, we want to read from location 0D. So we have to turn the LD pin from a 0 to a 1, and now we have a problem. Okay, when you see a wire that is red, you can click it to find out what is wrong with it. So when you click it, it says 0E000EE0/error. The E in this case is because there are two things trying to drive that thing, drive those particular bits, and they do not agree. Because the input pin is trying to drive the bit 6 to a 1, but the memory module is trying to drive that bit to a 0. Same thing applies to bit 1 as well as bit 2. Is that okay so far? Does everybody understand when I said, is it okay? I meant, do we understand what is happening here? This is also known as a bus fight. Okay, so when you look at what is a bus is really just this is a bus, this is a bus. So a bus is basically just multiple individual conductors on the motherboard that serves a particular function together. So the data bus in this case has 8 individual traces or wires, however you want to call those. But those 8 things function as one together because they are all trying to specify the address that you're trying to tell the RAM. And then the data bus is the same way. So a fight has to do with more than one components is trying to specify the content of those wires, and they do not agree. So in this case, it's a bad situation because whatever is driving the input pin is fighting with your RAM. In other words, current is going from the input pin straight into the RAM, and they are having a tug of war at this point. Which also means each component is going to drive as much current as it possibly can because it wants to win. Which one do you think is going to win? All things being the same, whichever one is specified as 0 usually wins. It has to do with N-channel MOSFETs have more driving capability than P-channel MOSFETs. So it's just a physical thing. You know, when you go to a device physics class, I guess you will understand more about why it is easier to sink current than it is to source current. Okay, sourcing means you're pumping out, and sinking means you're sucking in. Okay, but nonetheless, this is a bad situation. We don't like situations like that. So what do? We have to kind of like, okay, maybe we have to disengage the input pin when this is a read operation. Is that making sense? In other words, we want to make this particular wire kind of, sometimes it's here and sometimes it's not here. That's what we want. So let's take it out first, and then we check out the components and go like, okay, let's see who can do this. Let's check out gates. Okay, when you check out gates, it has got a controlled buffer, and that's exactly what we need. A controlled buffer, okay, I'll put it here first, and then we'll go to the documentation. Okay, so we go back here, we go back, it is under gates, control buffer. Okay, behavior. The control buffer and inverter, we're not using an inverter, but the only difference is an inverter is basically a NOT gate, but it is also controlled. So it's got one extra pin. It is not just a regular NOT gate in this case, or just a regular, we call this an amplifier. This pin in the middle is the one that controls whether the output is driven or not. When the value of this pin, which is the one in the middle, is a 1, then the component behaves just like a respective component, either a buffer, which is basically, the identity gate, if you want to call it, or an inverter, which is a NOT gate. When the value of this pin is a 0, then it is disconnecting. The output is no longer driven. Is that okay? How many people here drive a 6-shift or know what it is? Okay, that's a clutch. Okay. So your car can be rolling backwards and you're in first gear, but as long as you're pressing down the clutch, that's not a problem. The moment you release the clutch, especially when you put on a little bit of gas, then you have a bus fight. Because the car is rolling backwards, but your engine wants to go forward, and then the gear is going to grind. Is that okay? So a buffer is basically a clutch. It allows you to disengage whatever is the input, so it's no longer driving the output. So the output can be disabled. Is that okay? Call it a kill switch, call it whatever you want to call it, but that's just a behavior. So in this case, back to our logic sim diagram, we need something like this. To be more specific, we need something like this so that we can, okay, it needs to be a multi-bit, 8-bit version of that. Okay, that we know. Okay, so we need the other side to connect to this part here. Okay, and we have a problem because it is now, by default, it is driving. By default, it is actually saying, yes, whatever is the input, I'm going to drive the output. So what we need here is to specify, how do we turn it off? We should turn it off now. What do you think?
You connect to the LD.
It relates to the LD,
Yeah.
but LD is a 1 right now. If I connect LD straight to it, it's going to turn it on.
Put it on.
Negate it first. Right, exactly. Okay, so that's very good. Good idea. So we just use a NOT gate, negate the LD, and then use that negated LD to specify the clutch. So now the clutch is fully depressed and it's not causing a problem anymore. Is that part okay? Cool. All right. So can we say we have a pretty good idea of how RAM operates at this point, or are there any questions about any one of these pins, or any questions about how do we do da 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 da? Is that okay? All right. Okay. So we only have one more component to talk about before we can actually present the processor. So according to the notes, okay, and we get back to, I just closed the tab that I wanted to get back to. That's okay. And it wants me to log in again. Okay, modules. And we want to, the next thing we want to talk about is a MUX and a DMUX. Okay. These are industry names, they're basically, abbreviations of the actual full name. So when we look up a MUX, there's no such thing called a MUX. It's called a multiplexer, okay, which otherwise is known as a MUX. And a DMUX, there's no such thing as a DMUX. It is called a demultiplexer. So if you have noticed already, in a certain era, people like to make new words out of existing words. Like the word modem, what does it mean? M-O-D-E-M, which is modem. Okay, how did we create that word?
Isn't it from modulator, demodulator?
Yeah. Yep, it is modulator, demodulator. That's exactly what a modem is. But they made up terms like that, and MUX and DMUX are kind of like that. They're just abbreviations of a much longer word, and then people just say, okay, we'll just call it multiplexer of MUX. Okay. All right, so we'll take a look at the documentation of a MUX in the browser because I got everything here already. So you go to plexers, and then you click on multiplexer. And here's the picture of a multiplexer. I'm not going to read the text here because the picture actually is kind of self-documenting in a way. So a multiplexer, when you look at the documentation of Logicin, most of the time the input is on the left-hand side and the output is on the right-hand side. Okay, so that part is pretty consistent with how the documentation goes. So in this case, we have 4 inputs and 1 output using that particular standard. Is that okay? So we got input, and you can see one input is labeled 0. Okay, so it's input 0, input 1, 2, 3. Okay, and there's one single output. What do you think this device is going to do? It's a switch. All it is going to do is like a railroad switch, and depending on what you specify here, with the port that has a dot on top of it, it will connect this one to the output, connect this one to the output, connect this one to the output, or the last one to the output. That means whatever has a dot here, what do you think is the width of this particular wire? Because you can only select 1 out of the 4. 2 bits. So if you have 0, 0 presented with a dot, with a gray dot, then it will select the first one. If you have 0, 1 specified here, it will select the second pin of the input to connect it to the output. If you select 1, 0, it will be the third one. If you select 1, 1, it will be the last one. In other words, it's kind of like indexing, right? You have 4 things in an array, and you have an index in the square bracket. So the gray dot is what you put inside the square bracket. And the input is your array. The output is the value of the element that you want. Is that okay so far with that analogy? Because you're selecting one of the 4 possible things. Yep.
What's the little blue thing next to that?
Aha, the blue thing. The blue thing is optional. So what you're referring to here is the blue thing next to the gray dot. The blue thing basically says, am I enabled? It is EN, okay? Or SEL or select. So when this blue thing is a 1, then the thing operates as I described. If this blue thing is a 0, then the whole thing is turned off. So it is basically a combination of a MUX combined with a buffer that we just talked about. Is that okay so far? Does everybody understand what that blue thing that I'm pointing at right now does? It's a clutch, basically. If the clutch is a 0, then the MUX is not going to output anything. regardless of what is selected. But if the blue dot is a 1, then it functions just like we described. And it is optional. You can take that pin out in Logisim and just say it's always outputting something. All right. So are we doing okay so far with a mux? Multiple input, pick one to become the output. That's basically what it does. With the option of not outputting anything at all. Okay. So what do you think a demux would do? The reverse of that, exactly. So the demux look exactly like the opposite of what we saw. And it functions just like that. You have one input and you have 4 ways to output it. Okay? And the gray dot, once again, is selecting which output is going to have the content of the input. Okay? And the blue dot, in this case, is interesting because the blue dot is also specifying, if should I drive any one of the 4? If the blue dot, let me put the mouse pointer on it first. So if this blue dot is a 0, then it's not driving anything. The whole thing is quote unquote turned off. None of the 4 output will be driven. Otherwise, one and only one of the output will be driven, and it will specify the same content as the input. Is that okay? All right. Well, I lied. There are actually one more thing that we need to know. It's called a decoder. But a decoder, if you look at the decoder, what does it look like to you?
It looks like a plexer without.
It looks like a demultiplexer without the input. Exactly. What do you think that assumed input is going to be? A 1.
Oh.
Yep, that's it. So a decoder is basically having an implicit input of a 1, but otherwise it behaves just like a demultiplexer. Okay, and you might wonder, yep, go ahead.
I'm just curious, if that's the case, then can't we just get the demultiplexer and just have an input pin that just has 1 and then just put it in and then it'll function the same?
Then becomes a decoder. Yep. So you can also read the behavior. It emits a 1 or outputs a 1 or specifies a 1 on exactly one output. Which output is 1 depends on the current values received through the input on the south edge, which is the gray dot here. And then the other pin, which is this pin here, is south edge left side is enable. When enable is 0, all output consists of all floating points, or floating bits, or zeros, regardless of the select bit. Okay, so are we doing okay so far with all of this stuff? We good so far? Okay. Next thing. Yep, go ahead.
Can you make them have more splits or is 4?
Oh yeah. Yeah, you can select, I cannot remember the upper limit, but they can, it has to be at least 2, because if one bit demux doesn't make any sense, or one output demux doesn't make any sense, so you can go from 2 to some pretty big number. Okay. Yep. So are we doing okay so far with all of these things? How do we do this with transistors? Okay, let's maybe just AND gates, OR gates, and NOT gates. Can we do a, let's start with a demultiplexer, okay? And we'll make one that doesn't have a buffered output, so it's always on. Yep.
You need the splitters, right?
A splitter?
If you're using
No, you don't need a splitter, but you do need a whole bunch of AND gates.
Oh,
Yep. So let's check out what to do. So this is something that you would also learn in many other classes, especially when you're going into a computer engineering or electrical engineering class. They will talk about all of this stuff here. Okay, so what we'll do is we'll say we have an input pin. Okay, so input pin. We have the selection, which is 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, and 1, 1 for 4-bit demux. And then we have the out here. Okay. We have out 1, out 2, out 3, and out 4. Okay, there we go. So when the input is okay, it's X here, 0, 0. So this wants to be this needs to be X, and we'll just call out all of these zeros, okay? When cell is 0, 1, we want this one to be a 0, this one to be X, all of those other ones to be a 0. When the select is 1, 0, we want 0, 0, X, 0 here. And when the select is 1, 1, we want the last one to be an X. Okay, so this is sort of the truth table of what a demultiplexer should do. Okay, are there any questions about this particular table? I'm just making the assumption that if you're not selected, it's all going to be zeros. Okay. So now the question is, how do you make an equation to do all this? So out1 is going to be what? How do you want to define out1, which is going to be the input when both select pins are zeros. So let's say we separate select into cell 0 and cell 1. So cell 0, cell 1. When both of these are zeros, we want out1 to be in. So that's the equation for out1. Does that make any sense? Because only when cell 0, which is bit 0 of cell, and cell 1, which is bit 1 of cell, when both of those are zeros, the negation of both of those would be 1s, and then the conjunction would be a 1. So only in that case, the input pin would be, the out1 would be the same as the input pin. So out2 is going to be in, and then we have a conjunction, in this case with not cell 0, cell 1. Out3 is going to be the other way around, cell 0, not cell 1. I think I got it flipped. Yeah, I got it flipped, sorry. I got it reversed. Because this is the more significant bit, so I got it flipped. So out4, and by the way, this is a bad way of naming it. This one should be out 0. Yep. My band-aid is, I'm blaming on my band-aid. Okay. 0. That's the other hand I cannot blame you on the band-aid. Okay, so in this case would be cell 0, cell 1. Okay, well, it seems like, okay, if you want the output not to drive something, then you need to also have the buffer thing and specify what the buffer is supposed to do. But the whole thing can be done using just AND gates and a controlled buffer, or components, of those. So are we doing okay so far with this? Okay, cool. All right, so I think we are ahead of schedule. I was not expecting this all to be done within 15 minutes. So pretty good. Are there any questions before we move on? Because once we have all of these components, now we have to look at the bigger picture of what a processor would look like using all of these components. Yep.
So all the cells are connected together by conjunction.
Yes, well, they are all conjunctions, but with some negations. At the input of the conjunctions. Yep.
So is there a way to use these to extract one wire instead of using a giant splitter? You have a bunch of stuff in the wire.
Right. A splitter is not conditional. So a splitter is only good when you have multiple bits coming in, and it splits the multiple bits into individual bits. So for schematic purposes means for drawing it out the diagram and stuff like that. A splitter is useful, or a merger is useful, because instead of routing 20 gazillion lines from one place to another place, you merge all of them in one single wire. You just have one wire to connect, right? So splitting and merging is really only for documentation purposes. It's for the convenience of documentation, just like tunnels are. But a demultiplexer is functional. It is allowing you to have one single input, and there are 4 possible destinations, and you go like, okay, which one of these 4 should get this input? Or in the case of a multiplexer, it is the other way around. You have 4 sources, 4 ways of things coming in. but only has one single destination. So it allows you to specify, okay, who should be getting one of these 4 inputs. Well, you know who's getting it, but where is it getting that input? You allow it to switch. Yep.
Is it weird, or should out 1 and 2 be flipped? Because wherever it's a not cell, that's a 0, right?
Right.
And so in our cell for out 1, it's 0, 1. But we have.
That's correct.
That's correct.
Because 1 is the more significant bit. So we have 0, 1.
Well, isn't it supposed to be from the left 0?
Well, but this is bit 1. I should have said cell. If I should have put it the other way around, so that the more significant bit is on the left hand side. But 1, specify this is bit 1 instead of bit 0. But you're right. I just did not follow the convention of more significant bit to the left. All right. So I think you guys are ready to take a look at the processor. So let me go grab that and share that with the class. It is all on my Google Drive already. In fact, I have one single folder on my Google Drive that has all the shareable files with the class. So I'm going to share that with you guys. So let's see. Okay, the name implies this is all shared. So I'm going to click just share the entire thing, and then inside it there has a lot of subfolders. Okay. And get back to here. I will put it all the way to the top. It's not exactly syllabus, but I don't have anything on top of this, so I'm going to put it here. External URL, paste, shared folder. All right, so now you guys have access to the shared folder. So once you get to the shared folder, it will look like this. It has got a lot of stuff. And when you go to processor, you will see all of these files. One particular file, or there are several files you need to get in order to get the processor to work. So I'll show you which one. This is one of them. It's processor WDPC2. Okay, the name is it's named that way for a certain reason. And then the other one is I'm trying to register bank, which is this one, and there's one more, which is the ALU. So I think it's down here. There we go. So those 3 files are the ones that you need in order to kind of at least take a look at the processor. Just getting these 3 files, it doesn't really do anything. It won't work. But at least you can look at the schematic and say, oh, okay, we got all of these components. This one here, this one here, this one here. Okay. So with these selected, I think I can download just once. So download, and it's going to zip it first, and then we'll download the zip file, and then we just unzip it once we get it. All right. Here we go. Save to. I don't want to put it into the temp folder. I'm going to put it into my home folder. There we go. Okay. So now that we have this in my home folder, I'll just make a new folder called processor. It's already there. That's okay. Question is, do I want to remove it? No. I want to make a new one. There we go. So inside this folder, I'm going to unzip the file that I just created, and it's in my other folder. What is the name of that? There we go. Drive download. Okay, there we go. All right, so we got the 3 files here, and once we get the 3 files, the one that you want to open is processor WDPC2. Okay, because once you open that one, it will try to include the other one. It doesn't know where to find it. It will complain about it. You just have to tell it, okay, this is where you find reg bank or register bank, and this is where you find ALU. So let me show you exactly what's going to happen when you try to open. So we will say new or just open, and then we go to the processor 17 folder, and then we open processor WDPC2. Click open. Then it will say if the other two files are missing. That's okay. Just click when it asks for ALU. Click on ALU. When it asks for register bank, you click on register bank and then click select. And now we have the actual processor. Oh, this is actually pretty simple. Okay, trust me. This is as risky as it gets. Okay, so we have this whole thing. Scrolls a little bit. Okay, not too bad. Okay, it's not too bad. Trust me, this is not bad at all. And then you look into the components and you go like, okay, what is this? So you right click and say view register bank, and it's its own little thing. Okay. And then you go to the ALU and go like, what does it look like here? You say view ALU, and that's the ALU all by itself. All right. So, really bad? It's not too bad. It's only bad because I zoom in too much and I have a limited resolution. If you zoom out, see, it's not too bad. Okay, so with all of this stuff here, where do we start? Well, let's start with the ALU. Okay, the ALU is what is doing all the computation, so it seems like it is of some significance, right? So we'll take a look at the ALU all by itself. If this is your objective, you can actually just open ALU by itself too. So if you open the ALU, it looks like this, okay? So it looks kind of, yeah, what is that, right? Okay, so we'll take a look at, you can see there are two muxes here, and there's one demux here. Let's just zoom in to the top part here. Now can everybody in class still see as far as I can kind of pull this? Because the back of the class can't really see at the bottom part of the projector. There we go. So I think this is probably a good magnification. I can magnify maybe one more step. Too much. Can I enter a number? Nope. Okay. Okay, so we got input 1 and input 2 because most operations that you want to perform requires two operands. Addition, two operands. Subtraction, two operands. Bitwise AND, two operands. Bitwise OR, two operands. Bitwise NOT, just one, okay? But shifting needs two too. So that's why, for most operations, we got two input pins. So we have these two demuxes. Remember what a demux is? You have one input and you have multiple output. So in this case, we have one input and we want to feed that input to one of the output. So you can see that the gray dot here. Now these two, they share the same gray dot. Do you see this part here? Let me click on the wire itself. There we go. So you can see how those two muxes, along with the demux and the mux, they all share the same gray dot. And all of those go to OPSEL, or operation select. Okay? In other words, OP select, operation select, is telling the ALU, what are we doing? Are we adding? Are we subtracting? Are we bit shifting? Are we doing bitwise OR, bitwise AND, or what? Okay? Yep.
What else is it going to?
It also goes to the mux for the flags, for the overflow, and for the carry, because when you are dealing with carry and overflow, it depends on whether it's adding or subtracting. So that's why it needs its own little switch over there. And I think that's it. Yep, that's it. That's all it goes to. But we'll focus on just addition and subtraction. Okay. So the two demuxes, these two, their purpose is to say, are we adding? If we are adding, then this signal should go here for adding, and then this signal should go here when we are adding. Okay? If we are subtracting, then they should go to the subtractor, and also the other one should go to the other wire of the subtractor. So that's why we have those. But when we get the results, we also want to know, we also want to indicate which result from which thing should we use as the actual output of the entire ALU. So that's why the multiplexer, which is controlling the output of the ALU, is connected to the same operation selection. So they're all synchronized. Is that okay so far? And that's pretty much what the ALU does. There's an ALU enable, which is this one here. So ALU enable is enabling all of the muxes and all the demuxes. The idea of the ALU enable is only to save power. Okay, when you're not actually doing any type of operation, let's turn off all of these circuits. That's what it does. But it also stops driving the output so that whatever we are connecting the ALU to can now be driven by something else when the ALU enable is turned off. So we still do okay so far with this picture, the ALU. And then we got some really kind of weird stuff coming in. We got a tunnel called S2. You see the S2, S1? S1 is all the way here. S2 is all the way here. If I magnify, you can probably see how we split the wire to get to S7. So let me magnify one more time. So what is S1 according to the splitter? It is bit 7 of in 1. How many bits do we have for the input pins? 8 pins. So bit 7 is also known as, why do you think I used the letter S?
The sign bit?
The sign bit. Okay, very good. So we have the sign bit of the first operand, and then we have the sign bit of the second operand. What do you think requires the sign bit of the operands?
Addition and subtraction.
Addition and subtraction can do that, but but we don't need to split it out by itself, right?
Like multiplication or something?
No. One of the flags that we have talked about when we talked about comparison of signed numbers. The overflow, very good. Okay, good job. So the overflow is what needs this one and also this one here. So when you follow the tunnel, when you click on the tunnel, everything that uses this tunnel or this particular node will be highlighted. So let's check out this particular circuit here. What do you think these things are? The first one seems to be suggesting not S1, not S2,
It's overflow.
but S out.
Yeah, it's overflow.
It's overflow for addition. And then the other one, which is S1, S1, S2, not S out. Excuse me, I take it back. Not S1, S2, S out. What do you think that one is specifying? What do you think this gate is doing? Highlighting the gate itself. So it's basically saying when the first number is not negative, the second number is negative, and the result is negative, then we have a problem. It's overflow. So that's part of the definition of overflow for addition or subtraction.
Subtraction.
For subtraction, exactly. And that is why the output of all of this is connected to the second wire or the second input of this multiplexer. Because when OP cell, the operation selection is a 1, we're specifying a subtraction. So that's why the overflow flag should also reflect the overflow status of the subtraction. Yep.
Why does it say you cannot modify the circuit?
So take
It says you can't modify the circuit. Why does it say that?
Oh, cannot modify
Yeah.
circuit because it is a subcomponent right now.
Oh, okay.
So you have to modify the actual file containing that definition.
And why are all the wires red? Is that just because of?
They are red because it's not specified. because S1 is actually not specified right now. It's floating. So when you have a okay, that's a good question, because you can see that one AND gate is okay, outputting an actual low. The other one is not okay. So why is that? Well, because with this one is an AND gate, right? With an AND gate, if at least one input is a 0, the output is guaranteed to be a 0. So logic sim is smart enough to use lazy evaluation and then figure out, oh, okay, the output is going to be a 0 anyway, so I don't have a problem with that. But when you look at the second AND gate, which is this one here, the first input is unknown. Okay, we cannot depend on it, right? The second input is a low, but it is negated, which is a 1. When you have 1, 1 with an AND that has 3 operands, you don't know what the output is supposed to be, right? But the third one is unknown also, which means I cannot really tell whether the output should be a 1 or 0, and that's why it is red, because it cannot be determined.
And why is S1 floating but S2 isn't?
That has to do with. Remember, you asked. That's because.
Oh no.
That's because of the way these things are doing things. Because this mux. Okay, this mux currently has a 0, 1. Excuse me, take it back. The gray dot is a 1. Okay, so it is selecting this one to be the input. So it has something is driving that input. This in one, okay, let me switch back to this tool. So this one is coming from this demux here, but this particular demux is disabled because RO0EN is disabled. So nothing is driving any output of that mux, and as a result, in one of the ALU right now is not driven; it is just floating. So that's why it's causing problems inside. Good question. So is that okay? Do you guys have a general idea of how the ALU operates? Yep.
I was just wondering if you could feed it something to make it work.
Yep, you certainly can, but not in this particular picture. So if you want to play with the ALU by itself, you can just look at the ALU by itself. So when we open just the ALU by itself, select, open, there we go. So now we can actually play with it. Okay, you can specify, let's do something plus something. So we will say, let's do subtraction, okay? 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, minus 1, 0, 0, 1, 1, 0, 0, 1, okay? That's what we want to specify. But remember, it's a subtraction. When operation selection is 0, 0, 0, it is specifying addition. So you need to turn this into 0, 0, 0, 0, 1 to be subtraction. But the whole thing is turned off because ALU enable is a 0. So that means everything is turned off. The demultiplexers and the multiplexers, they're all off. So you have to turn it on. And we should have something now, at least as a result. This is the result of the subtraction. And you can also see the sign bit of the output is a 1, okay? In fact, we can look at all the flags. The 0 flag is a 0 because the result is non-zero. And then the overflow is a 1 because the sign flag of the result does not make any sense. The carry, or the borrow in this case, is a 1 because the subtraction ends up with a borrow. Do you see how all the flags are coming back? Yep. So that's that's how the ALU works. Yep.
And what do all the flags merge into?
Just one single port, just for the convenience. So they all just merge into one single flags out port. Yep. Is that okay? But you can also specify other operations. You can look at the operators, all the things that you can do with this particular ALU. So I only specify addition, subtraction, bit shifting. This is only shifting to the right, as the arrow indicates. So only right shift has its own operation, but not left shift. left shift is not really needed because you can add a number to itself. Remember, I'm trying to make this as risky as possible. So I'm trying to reduce the number of components, and that's why I don't have the equivalent shift on the other side. Okay. This is bitwise NOT. Bitwise NOT is useful. This is bitwise AND, and this is bitwise OR. But this is not really as risky as it really should be, because remember, NAND can do everything. So if I really want to reduce these things, I can just combine these 3 logic gates into a single NAND tube, but then the assembly code will get a lot messier. So it's a trade-off. So are we doing okay so far with the ALU? Okay, the ALU just contains a whole bunch of actual operations, 2 demuxes to feed the operations, and then 1 single mux to select, okay, we want to report the operation of which operation again, and then send it out as the output. And then the flags are really just being done on the side. It has its own output, and also input. Are we doing okay so far with the ALU? Okay. So the next component is called the register bank. The register bank looks really kind of complex, but it's not. Okay, cancel that. We want to open register bank. There we go. So register bank looks kind of complex, but it is actually easier to understand because it's very, how should I put it? It's very, there's a certain geometry to it, okay, and that makes it very easy to deal with. So the core of a register bank is basically a collection of registers. So in this case, we got 4 registers. Let me point out which 4 we are talking about. So we got register 0, register 1, register 2, and register 3. In this class, we call them register A to D, okay? So we got 4 registers. But the purpose of a register bank is to give you some control over which one is the one that should receive, that should store whatever is presented as the input port, and which 2 should we use as the output. So what you see here is there's a register in port here, which is used to specify, oh, I want to update one of these 4 registers with this new content. But which one do we want to update? You have register in selection here. So this connects to the gray dot corresponding to this decoder. Remember, a decoder is really a demux, except the input is always a 1. Okay? So this allows you to specify which one of these 4 registers is updated, because the output of the decoder connects to the enable of each individual register. Is that okay? But when you look at the clock is common to everything. Do you see how the clock is connected to everybody? Okay, and so is register in. This is also multi-dropped. So the only thing that is not multi-dropped is the enable pin. The enable pin is connected to the decoder, and that is what allows us to specify, oh, only you should update, even though everybody is getting the same data presented on the D port, and everybody's getting the clock. Only one of them will have enable turned on at the most. Okay. What about this guy? What about register out 0 and register out 1? So as a bank, as an entire unit, you can specify up to 2 outputs. The reason why you can specify up to 2 outputs is mostly because of the ALU. Okay? If you want to add, you need 2 numbers, right? If you want to subtract, you need 2 numbers. If you want to do bit shift, you need 2 numbers, because one specifies the bit pattern and the other one to specify how many bits to shift. If you want a bitwise OR, you need 2. If you want bitwise AND, you need 2 as well. So that's why the register bank has 2 outputs as a whole. But which one should, question? No, okay. So, but which one should go to the first output and which one should go to the second output? Well, that's why we got the multiplexers. So this particular multiplexer is controlling which one goes to the first output pin of the entire register bank, and this one controls which one goes to the second output of the entire register bank. Okay, but you can see that, oh, so if I use 0, 0 here and 0, 0 here, then we are selecting the same register as the first output and the same register for the second output. You're absolutely right about it. We should not, there should be no restriction of you cannot do that. Is that okay so far? So the register bank, at this point only has 4 registers. Increasing the number of registers is advantageous, but it also makes your instructions wider, because you will need more bits to specify which register should I use as the first number to add, and which one should I use as the second input to the adder. Okay, and we only have 1 byte for the instructions, so I'm kind of confined by that as far as the number of registers that we can use. So are we doing okay so far with this? Okay, so getting back to the big picture. Sodor Island, the island of Sodor. Okay, let's close this one because we don't need to look at the inside of the ALU for now. And this one is just blank, I think. Get rid of that. Okay, the island of Sodor. So now we got, all right, so we have, this is the register bank, this is the ALU. And when you click on a wire, okay, such as this one, then you ask the question, how come this one is not always connected to out 0 of the register bank? You can see that out 0 is feeding into the demultiplexer, and this is one of the output of the multiplexer. So you want to ask, why is there a demultiplexer in between? What else do we want to use out 0 for? So you click on these wires. Oh, this one's going somewhere. This one is also going somewhere. This one is going to a place that is kind of interesting. Let's track down this one. This really kind of thick line here. And you can see this one goes to, scroll. Where does it go to? The component right here? RAM, exactly. So that one goes to RAM, which means it seems to us that we are able to use the output of a register bank to become the input into the RAM module. So what do you think that's going to be useful? What kind of operation requires the processor to drive the data port and the RAM module to read from the data port? When you want to change the content of RAM. So that multiplexer is useful because we want to be able to write operations. In other words, you only got 4 registers. What if your computation requires you to keep track of more pieces than 4 things? We store it in RAM. Okay? We are running out of time, but I do want to point out the other one. So what about out 1 from the register bank? So out 1 of the register bank, which is this one here, also goes to a smaller demultiplexer. Okay? One of them eventually will end up here. Okay? This one will eventually end up here. What about this guy here? This guy goes to another multiplexer, and this multiplexer goes to the address bus. In other words, I can use one register to specify which location in RAM, and I can use another register to specify the new content of that location. I can now random access RAM and say, hey, this register specifies which location to change. That other register specifies how to change it. Change it to what content? What is the new content? So it is because of all of these operations that we want to support that we have all of these switches. Remember, every time you see a MUX and a DMUX, it is equivalent to a switch in a railroad setting. Okay? So if this is the island of Sodor, you basically just have all kinds of train tracks everywhere. and you also have a lot of switches because you got depots, we got train stations, we got repair stations and whatnot. So you need to coordinate all of these things. But who's coordinating? In other words, when you track down, all of these control lines, okay, everything that controls the multiplexers and demultiplexers, they're control lines of some kind. This one is, this one is, this one is, and so on. They are all tunnels, because if I don't use tunnels, this diagram will look really ugly, okay? So all of these control signals eventually merge into U code data. U is micro, okay? This is micro code data. And that eventually gets merged into this whole thing here. And you can see that this ROM has 26 bits as its output. Because it is control. This is the central control of Solar Island. Okay, this is the one place that the fact controller is, doing all the switching. You go like, okay, you go here, you go here, you go here. But what is controlling that? It's a music box. It's a music box. In other words, in order to orchestrate the operation of the island, okay, Sir Topham Hatt is playing a music box, and he's doing dum 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 dum, and then and then the tracks got changed, and then the whole island would do everything in a synchronous fashion. But the next operation, which is from somebody else, may change the tune, right? So he would go like dum 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 dum, dum 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 dum. So a different tune means the whole island is functioning as a whole to do something that's different. Is that okay? I think the only thing you guys remember will be the tunes that I just hummed. Alrighty, well, thanks to Beethoven. So I'll see you guys over at the lab if you want to work on your homework assignment. But this is certainly something that I want you guys to spend some time on, because we have a long, like 5 days before the next class.